let's see an example of a system where we actually have real data. So life expectancy since 1980. Now, I assume there's going to be a huge dip in life expectancy since COVID. It is going to drop the average lifespan significantly. So I'm interested to see what kind of like life expectancy dip it takes for this. Anyway, we have some data from 1980 to 2005, and I think it's worth looking at. So here was the life expectancy for these years, people in the U.S., and according to their gender. So this is gender that I'm not sure how they picked gender, whether they, this was, it's life expectancy, which means this is usually just recorded upon death. So, yep, I don't think it has anything to do with how you identify at all. So, and how somebody else identifies you there. So, just to let you know about data. Use your calculator to write linear equation for life expectancy of women since 1980. Okay, so we're going to look at, first, we need to pin down what is the explanatory variable and what is the responding variable. So I believe that time is independent of men and women. So people in general, all people. So here, this is going to be our explanatory. So the year is going to be explaining the length of the average person. So these are both responding variables, and this responds to what year it is. All right. So I have gone ahead and put in this data, except we better put this as years since. So years since 1980, that is 0 years, 5 years, 10, 15, 20 years, and 25 years after 1980. Okay, let's do it. So turn this on. I go to Stat. I first edit, and so I need you to see that in L1 I put the years, and in L2 I put the ages of the life expectancy of women through the ages. And then I'm going to go back to Stat, but now I'm going to go over, so I'm going to arrow over to calculate and go down to 4, linear regression, and hit enter. L1 is my explanatory variable, L2 is my response, and I'm going to calculate this. Okay, let's write that stuff down. All right, it says that the A value is about 0.12. So that's our slope. Let's see. I'll write it with y's first. Y is approximately 0.12x plus 77 point, I rounded to 2 decimals, so I'll do the same for 5. But I still don't like x's and y's. They are just too abstract for me. So this is women age. So we're going to go women. Oh, it's data-based, so there's always error. And I rounded both of these. Is 0.12, and what is x? Ooh, years since 1980, so that's t. Okay, so that's really a t for time, plus 77.45. Got it. What is the correlation coefficient? Here, R was approximately 0.972, which is 97.2%. It's pretty strong, yeah. Is this a linear relationship? Yes. These are strongly correlated. Got it. life expectancy and the year and time. Okay, let's do this again, but now we'll do it for the men. Okay. Okay, I'm gonna clear actually. And then I'm gonna go stat, calculate. So I'm using this down arrow, enter. Now I still want the years since to be my explanatory, but now this list, remember that list was for women, and let's see, where's L3? Right there. Oh, do I have a little bit of, okay, sorry about that. I can see it. Right there, L3. So I'm going to go second 3 and change my response to the men list. Hit enter, and I have all of the things I need to know. Okay, so what is this? Y is approximately, round this to 2 decimals, 0.21x plus 69.9. So this would be, the men's age is approximately 0.21x plus 69.9. Got it. What is the correlation coefficient? That is 0.978. Even more linear, a little bit. Is it a linear relationship? These are strongly correlated. So yes, I would say. Based on the data, predict the life expectancy ages of women and men in 2022. Oh, right. Okay, so they're giving us a time. But remember that T is years since 1980. So 2022, how long is that? So 2022 minus 1980. The difference is 42 years. It's 42 years later. Oh yeah, that makes perfect sense. From 1980 to 1990, to 2000 is 20 years, and then there's 22 more. Got it. If T equals 42, then I can put it into both of these and see what's happening. I'm going to do them in their colors. So, women's life expectancy, oh boy, it's definitely not going to fit this model anymore. But the interesting part is, will I be able to actually see it? Because we have these models now. Made them in this class. So women's life expectancy, 0.12 times 42 years plus 77.45 initially is about 82 and a half years old. Okay, and then let's go men's style. So predicted average life expectancy. 0.21 times 42 plus 69.9. The men's average life expectancy, 0.21 times 42 plus 69.9. In my calculator, 78.7. Okay, years old. In 2022. Now, write a system using these two equations and solve it using the substitution method. Got it. What was it? Women was about 0.12 T plus 77.45, and the men's equation was about, okay, 0.21 T plus 69.9. Okay, I just wanted to copy it right because that otherwise would be a big disaster. Okay, and now we set them equal. We set these two equations equal and figure out what that means. Okay, let's solve it. I'm going to go ahead and subtract 12/100ths of a t from both sides. So we would have 77.45 on the left. What is that, 0.09? Yep. 0.09 t's plus 69.9. I'm going to subtract 69.9 from both sides. So 0.09 t, let's see, 77.45 minus 69.9. I get 7.55. And now I'm going to scale down. All right. So undoing this multiplication times t, if I divide it, then t stands alone. And 7.55 divided by 0.09. Oh boy, that has to be approximated and rounded. 83.88888888. So about 83.9-ish. Okay, but that's t, right? So that deals with time. And now we have to find the age. Okay, so let's put that t into the equation. 0.12 times 83.9 plus 77.45. So the women age and the men age would be about 87.5. Okay. So here's our solution. Remember, there's two equations, and so we have two values here, the time and the age, both women and men. What does this solution mean in the context of the situation? Well, both men and women, not to leave others out, will have an average life expectancy of about 87.5 years old. Okay, and this is about 84 years after what, 1980? Yep, sure was. So I'm going to add 84 years to that. 2064 and 2064. But again, I mean, pandemic style, that's probably going to be way off. So let's talk about a few things that happened. And just a couple of remarks about when this could go wrong. So first, lines that are parallel, they will never meet. And so there will never be a solution to those scenarios. So, so they just literally have no solution. They're unsolvable. I don't know if that's a real word, but anyway. So if they're parallel and never meet, then there's no way to find their meeting point. They just are unsolvable problems. Okay? And then another remarkable thing is that sometimes people don't realize that they have given they've given within their system an equation to model one piece of it and then another, like, added information to look at another piece of it, and then come to find out they are the same piece of information. Okay, so lines that end up being exactly the same, are scenarios where anywhere along that line is a possible solution. So lines that end up being exactly the same are the situation where there are many answers, many possible solutions. Any pair along the line will work. Okay, so there are situations where you can have infinitely many solutions, but not just whatever you want it to be. They have to be a pair along the line. But then there are definitely problems out there where there's no solution whatsoever. They're not solvable. And then, lastly, of course, there are two lines that can intersect at exactly one spot. So lines that intersect have exactly one solution where they meet, but remembering that you have to have both values in order to consider your system. The year and the age, yes? Two things working together. So, just to look back, right? Our job was to set up systems. We did that. Find solutions using the graph, and that's where they intersect. Finding tables, and that's where they all are the same. So, well, the y values are exactly the same for the same corresponding x. And sometimes we like to use substitution where we set the two equations equal and solve those algebraically. Recognize when an ordered pair is not a solution and when something is a solution, and interpret it. So, the last section of this chapter, systems of equations, graphs, tables, setting them equal, and then writing what it means. Remembering that there are two values for any solution to a system.